Assalamu alaikum. Today we are going to solve this problem. We have a positive point charge Q. This is the point charge which exists at the center of a spherical dielectric shell, and this is spherical dielectric shell. Okay, this region is the only region which is filled with the dielectric material. Okay, otherwise is a vacuum. Okay, and as we see, this spherical shell is restricted by this inner radius r sub I and an outer radius r sub O. And the dielectric constant of this shell is equal to epsilon sub r. And from this problem, we are going to determine the electric field, the electric potential, the electric displacement, and the electric polarization. And the methodology that we are going to pursue in order to calculate these four electrical quantity is firstly calculating the electric field by using Gauss's law. And yes, Gauss's law is applicable in this case because we can construct a Gaussian surface around this shell, and this electric field that we will calculate from Gauss's law, we are going to use to calculate the electric potential by using this equation, and the electric displacement by this equation, and finally the electric polarization by using both the electric displacement D and the electric field E. Let's start from this problem. You can notice that the electric field will be different between these three regions because we have bounds determined by R sub I and R sub O. So firstly, I'm going to determine the electric field at this region, at the region outside the spherical dielectric shell. And for this, I'm going to construct a Gaussian surface, which is this brown colored sphere, in order to find the electric field from Gauss's law. Gauss's law is where ds is the differential area of this spherical Gaussian surface, and the result of this integration is equal to E times the area of this spherical shell, which is, let's say, A. Okay, I'm going to divide both sides by A, and as we said, this A is representing the area of the spherical Gaussian surface, and the area of the sphere is equal to 4 pi times the radius. Okay, and R is the radius of this Gaussian surface, and it's also representing the distance between the point charge which exists at the origin and some point outside the spherical shell, and this is the electrical field for the region. Okay, for the region when R is greater than R sub O. Okay, and as we said before, the electric field is variant between these three regions. Okay, so for this, I'm going to use the subscript E1, okay, to distinguish between the electric field inside each region. Okay, now let's find the electric potential. The electric potential is equal to the negative of the line integration for the electric field. And the bounds of this integration is infinity and R. And we use infinity as a reference. Now, this dl is the differential length. Okay, this is equal to the algebraic summation between the differential length at the three coordinate system, and in this case we are handling the spherical coordinate system. Then dl is equal to, when we make a dot product between the electric field and this differential length, these two components are going to vanish, are going to be eliminated, and we will end up with only this one. So we will have at the end, and I'm going to substitute the right hand side of this formula for E, and I'm going to eliminate this negative sign by changing the order of the bounds. Okay, and as we see, R exists in the bounds of this integral. So I'm going to use R prime as a dummy variable instead of R. Anyways, I'm sorry, I forgot this r squared right there. Okay, I forgot this. Okay, and then we have squared. Now I'm going to integrate, and the integration of 1 over r primed squared is equal to minus 1 over r. Okay, now plug infinity for r primed and we will have 0. Now plug r and we will have this result. At the end we will have this result, and this is the electric potential, and this is the electric potential in this region, V1 Q over 4 pi epsilon r. Now let's calculate the absolute permittivity is equal to the relative permittivity R times the permittivity of free space, which is epsilon. Okay, and the relative permittivity of the free space or vacuum is equal to 1. So we will end up with Q over 4 R primed. We just eliminated epsilon sub 0 from the denominator, and I'm going to use the subscript D1. Okay, now let's calculate the polarization. To find the polarization, we will subtract epsilon sub 0 E times E from the electric displacement. Now substitute the right hand side of this equation and the right hand side of this equation for D and E respectively. And by cancelling epsilon sub 0 out from the denominator and denominator, we will end up with 0. The polarization vector is equal to 0, and physically this is correct because in a free space we have no molecules in the first place in order to polarize and construct a polarization vector. Now we are going to find the four aforementioned quantities for the new region. I'm going to find now these quantities when R is greater than R sub I and less than R sub O. Or namely, we are going to find these quantities for the region for a point inside, for the point exists at the dielectric shell itself in this region in between. Okay, first let's start with the electric field. We are going to use again Gauss's law, but notice that in this context this region, okay, is dielectric. Okay, it's not free space, so the permittivity here is not only the permittivity of the free space. We must add a new, we must have the relative permittivity, okay, or the dielectric constant for this material. Okay, this integral will yield E times the area of this Gaussian surface. And I forgot to say that we will do the same procedure that we did before. We are going to draw a new Gaussian another Gaussian surface at the region between there. Okay, is equal to, and the electric field is equal to Q over epsilon sub 0 times epsilon sub r times A, or the area of the Gaussian surface. The area of this Gaussian surface, like what we aforementioned before, is equal to 4 pi times r squared, where r is the radius of this Gaussian surface, or the distance between the point charge and some point inside the dielectric shell. Okay, and for the quantities inside this region, I'm going to use the subscript 2. I mean, the electric field in this region is E2, and the electric potential in this region is V2, etc. Now let's determine the electric potential. We said it's equal to, and as you see from this integration, from this integral, we are going to find, we are going to integrate the electric field, okay, from R. This is, okay, this point is has distance of r from the point charge. So we want to start integration from this point to infinity. Okay, let's say that this point is infinity, and as we see, the electric field is not the same at these two regions. We have a discontinuity in the electric field. So this integral must be splitted into a couple of integrals. The first integral is between epsilon, between infinity and the outer radius of the dielectric shell, okay, which is infinity and r sub o, okay. And the electric field is this region we have determined before. It's equal to this is the electric field. This the electric field at some point outside the dielectric shell. Now the other part of the integral is between r sub o and r, and the electric field in this region, okay, the electric field in this region between r sub o and r, okay, is equal to this formula, okay. Now we are ready to take the integral, okay. What we are going to do right now is assigning infinity and r sub o for r primed in this formula, and I'm not going to waste your time with the basic algebra, so I'm going just to write the answer right away, directly. As we all see, we calculated the electric potential inside this region. Okay, now let's calculate the other vectors. And now we are going to find the electric displacement by this formula, the electric permittivity times the electric field. The electric permittivity actually, in this case, is equal to the product of the permittivity of the free space and the relative permittivity of this dielectric. So the final answer is going to be identical to this equation, but without these a couple of epsilons in the numerators. Okay, now let's find the polarization vector. The formula is determined previously. Just substitute the right hand sides for these two equations. And this is the final formula for the polarization. And there's something I forgot to add. I said that both of these quantities are vectors. So the unit vector for this is the radial unit vector a sub r, and the same unit vector for this a sub r. Now in the third region, in the third part of the problem, we are going to find the quantities when for some point inside this spherical shell, okay, for some point exists on the outer surface, on the surface of this spherical Gaussian surface, which is a brown color that I draw, okay. Let's start by calculating the electric field by Gauss's law. In this region, the only permittivity that we use is the permittivity of free space because it's hollow shell, and the answer is going to be like this. I mean, in this part of problem, I did not mention a lot of details while we are calculating the electric field, because the same monotonic routine procedure will be done again and again. So I am ignoring the parts where we are when we are repeating some things we did before. Okay, now we are going to find the electric potential from the electric field equation using the formula that we have expressed before. Notice that the electric field is a variant between these three regions that we have expressed before. These three regions are bounded by r sub I, r sub o, and infinity. Okay, let's now split this integral into three integrals. The first integral is between infinity and r sub o, okay. And the electric field in this region we have said before it's equal to E sub 1. And we have mentioned before in this video the formula of E sub 1. We have calculated it. We have times d r prime plus the second result is between r sub o and r sub I, and the electric field in this region between r sub o and r sub I is equal to this region between r sub o and r sub I is equal to E2, and the third region is between r sub I and r, and the electric field in this region, okay, let's say that it's equal to E3, and this is the electric field that we calculated before, that the last electric field that we have calculated, okay, and remember that when we calculated the electric potential for some point inside this region, okay, for some point inside this new region that I have drawn, and we called the electric potential at this region by V2, and it was a function of R, if you remember. Am I right? V2, and it was a function of R, and it was equal to the integral between infinity to R sub O, okay, plus the integral between R sub O and R. In this case, R is the Gaussian surface, the Gaussian surface before in the previous part of this problem was at this region when we was calculating the electric field, and the other quantities at this region, okay. The R was here, okay, so it was between R and R sub O. And notice that if we assigned R sub I for R in this equation, if we make R equal to R sub I, okay, we will end up with this part of this summation, okay? Am I right? By substituting R by R sub I. So this is equal to V2 when R is equal to R sub I, okay? And the formula of V sub 2 has been calculated before, and it was equal to over epsilon sub R times R, but in this case we are going to substitute R sub I for R, okay, R sub I, okay, this summation for these first two parameters, okay, plus this integral. For this integral I'm going to substitute the right hand side of this equation for E sub L in this equation, and we will have, and of course I'm not going to forget substituting R for the dummy variable R primed, because we have R at the bounds of this integral, and just solve this integral. I'm not going to waste your time with some basic monotonic algebra. You can do it yourself, and the final answer is going to be, and this is the formula of the electric potential for some point in the hollow region inside the electric shell. Now let's find the other parameters, which are the electric displacement D3 in this region is equal to epsilon times E3, and epsilon in this case is only the permittivity of free space. There is no relative, the relative permittivity is equal to 1, so it's equal to, now let's find the polarization in this region. The polarization is equal to D3 minus epsilon sub 0 times E3, and there's no need to plug all of these parameters to this equation. We know that this region is a vacuum, so the polarization is equal to 0 because there is no particles to be polarized in the first place. Okay, and by now at the end we found the electric field, the electric potential, the electric displacement, and the electric polarization at each region for this point charge which exists at the center of some dielectric shell. That's the end. See you.